Okay, welcome to video class 48, and you are on to the solution of time invariant state equation. And in this video, we will also be dealing with the state transition matrix, okay, and which is a very important topic under this module. Frequent questions are asked, so based on this. And not only that, in the next portion also, controllability and observability also, you require an idea about this. So this is a very important topic. So that is video class 48. Now, what is the meaning of the solution? Say, we know that, say for example, if you have a quadratic equation, say something like x square plus 2x plus 1 is equal to 0, what is the meaning of solution of this equation? Solution of this equation is you will be that is the roots or the values of x, so that this satisfies this equation. That's the meaning of solution. So since this is an equation, the variable x should have some values by upon which this equation gets satisfied. So similarly, when you talk about state equation, what is basically a state equation? We know that the matrix state, so do remember, the state equation is not an equation like a simple quadratic equation. This is a matrix equation, so that you all know. So far we have been studying about that. Okay, so we were representing various state equations of different electrical system, mechanical system, as well as different even from transfer function we were able to deduce the state equation. So all the state equations will be having a general form like this: x dot is equal to a times x plus b times u, right? Where a is called as the system matrix, okay, a is called as a system matrix, b is called as an input matrix, and your x dot is actually what is called as a state equation. Okay, now since it is an equation, we are expected to solve this. Okay, this is non, anyway the input is non, right? Okay, so from the given state equation, anyway this is a differential equation because the x dot always represents the first order derivative. So therefore this is going to be a differential equation, and solving a differential equation means, say for example, if you have a equation like this: d square y by dt square plus dy by dt plus y is equal to, say, some 3ax. If you are asked to solve this differential equation, means you are going to find out an expression for y of t. So similarly, you are going to find out a value for x. Okay, so that is what is called as the solution of a time invariant state equation. Do remember, it is not as simple as that of a linear equation, because this is x dot, a, b, u and x, everything represents a matrix. Okay, now how to solve this? This we know that x dot, capital X dot, is actually the derivative, right? It represents a derivative. Say for example, if it is the derivative, and if you know the Laplace transform of x of t to be x of s, capital X of s, what will be the Laplace transform of this? This will be s into x of s minus small x of 0, meaning the initial value of that function, time domain function. So you are going to apply the same thing here. So the first thing is, we want to find out the applying the, so this is actually the equation in time domain. This is the equation in time domain. Now what we are going to do is, we are converting it into the frequency domain. Now how to convert this into frequency domain or S domain? Frequency domain or S domain by applying Laplace transform. Call this as equation 1 by applying Laplace transform to 1. So anyway, this is x dot. So when you have this x dot, this will be s into x of s, right? S into x of s minus, okay, small x of or it is x of 0, means here you can call like this, it is x of 0, right? Or you can call this as a capital X of 0, meaning x of t. The meaning is x of t, this x of 0 refers to x of t at t is equal to 0, right? So s into x of s is equal to a into x of s plus, this is also a time domain function, this is also a time domain function, so this will be b into u of s, right? Now from this you'll be able to get this as, so you can take this x of s to this side, so that this becomes s into x of s minus a into x of s is equal to x of 0, that is the initial state, plus b into u of s. Now I can take this x of s outside. Now when I take x of s outside, okay, x of s outside, this becomes s. Now s is just a variable, it is not a matrix. Anyway, x of s represents a matrix. You are taking that matrix out, that means that's going to be an identity matrix, right? You know what an identity matrix is. So this is an identity matrix, its values, its diagonal elements of 1. So this is Si minus A itself is a matrix, so there is no point in writing A into I, because A into I is A itself, since A is another matrix. So this is Si minus A, where I refers to the identity matrix, which is equal to x of 0 plus b into u of s, right? Or now this si, s into I becomes a matrix. Si minus a is another matrix, right? So all these are matrix, so the result is going to be a matrix. Now how to find out that x of s? As in an equation, if it is, say for example, some a, or this is say some b, what you will write for x of s is x of 0 by b, b into u of s by b. That you cannot do here because it is a matrix. So what you do is, this will be keeping the multiplication rule of matrix, this will be si minus 1 into x of say 0. This is simple. Now assume that this is just a constant. If it would have been a constant, you will be dividing by b. I mean, say for example, call it as b. This will be x of 0 by b, b into u of s by 0. So when the matrix reaches over here, you should consider that as the inverse of this matrix. So it is equivalent in multiplying this matrix by its inverse, by si minus a's inverse. So si minus a inverse into x of 0 plus again si minus a inverse b into u of s, right? So that's it. Now from this you can take the Laplace inverse of this expression. Taking the Laplace inverse, what you will get is, so what is the Laplace inverse? So x of s becomes x of t, right? That is your state equation. State x of t is equal to, okay, this will be si minus a into inverse of x of 0, okay, so that is it's equivalent to x of 0 by s minus s1. What will you be writing for such a case? X of 0 is a constant. If you have 1 by s minus a, you will be calling that as e raised to s1 into t, right? So similarly, you can call this as this is s minus a, so this can be written as e raised to a into t x of 0 plus, what about this? This is s minus u of s by s minus a, or this can be written as b into, right, b into this is actually the this is actually what, actually Laplace transform. This is also Laplace transform. The product of the Laplace transform, this is actually the product of Laplace transform. So what is the inverse of the product of Laplace transform? It is the convolution of that. For example, say if you have x of s into y of s, when you take the inverse, it is nothing but it is x of tau into y of t minus tau d tau, right? So that means this is the convolution property of the Laplace transform. So when you apply the Laplace transform's convolution property, you will get this. So using that property, you will get this as 0 to t e raised to a into t minus tau, okay, into u of tau or d tau, but with a b, right? So this is b into e raised to a into t minus tau, b into u of tau d tau. So what is this? This is actually the uh, actually the convolution in time domain, right? This is the multiplication in frequency domain that results in convolution in time domain. So that is b times. So you can call this as, this is x of 0. What is this x of 0? X of 0 always represents the initial state, while this part consists of the input. So you can divide this responses into two. That is, one is, here you have the input is 0, so it is 0, that is u of, there is no u term here, that means the input is 0, so this is the 0 input response. While coming to this, there you don't find any x of 0 or anything of that, so this is called as a 0 state response. 0 state response. And the 0 input response is also called as the natural response, while this is called as a forced response. You have studied that in your signals and system course. So I again repeat, say we know that Laplace transform of so how will you get the inverse of this? The Laplace transform of Laplace inverse of 1 by s minus a is e raised to at. So I am just applying that here. The only difference is this is going to be a matrix. E raised to at is a matrix into x of 0. Okay, so which represents the 0 input response, the other one is st. So you can call this x of t as the state, that is actually your solution of the state equation, right? Solution of the state equation is found out to be this. Okay. Okay, now looking at this expression, you can see a matrix called as Si minus A inverse. I'm going to take that out. Si minus A inverse. So this is anyway a matrix. You might have understood this. This is an identity matrix. This is another matrix. So the result is going to be a matrix. Not only that, it is the inverse of this matrix. And not only that, this is in S domain. Right. This is a Laplace transform. Now if you can find out the Laplace inverse of this, what is that? I have just mentioned that it is equal to e raised to at, right? E raised to at. That is that frequency shifting property is simply applied. That's all. Okay, in the matrix form. So Si minus A inverse, the Laplace inverse of this is actually e raised to at, or this is denoted by the letter phi of t, and this is again a matrix, and this matrix is called as the state transition matrix. State transition matrix. So this is a very, very important thing. Usually this will be asked. Okay, so I will just recap again. We start with the state equation, apply the Laplace transform, and you have got an equation like this. We have found out two parts are there, that is a 0 input response and 0 state response. When you take the inverse of this is equivalent to x0 by Si minus A, or it's similar to 1 by s minus A. You're applying the Laplace inverse, you got this as e raised to at. Now from this I have taken this Si minus A inverse, and when you take the Laplace inverse of this, you will be getting e raised to at. That is again a matrix called as the state transition matrix. Okay, now this Si minus A inverse, that is the matrix, the inverse of this matrix, that is Si minus A inverse. Okay, if you can equate to 0, this is called as the characteristics equation, or which gives the solving this characteristic equation will give you the eigen values of the matrix. Okay, this will give the eigenvalues or the poles. As you all know, we have already studied characteristic solution of characteristic equation always gives you what? Always gives you the poles of that poles. Now, this Si minus A inverse, this matrix Si minus A inverse, this matrix is called as the reluctant matrix or resolvent matrix. Okay, so this is called as a reluctant matrix or resolvent matrix. Okay, so we started with the solution of state equation. From the solution we have defined what is called as a state transition matrix, and also defined what the characteristic equation. When you equate the state, it is the Laplace inverse of this thing. So do remember, it is not Si minus A inverse is not the state transition matrix, it is the Laplace inverse of this Si minus A, or Si minus A inverse is called as a reluctant matrix, or in other words you can say that the state transition matrix is the Laplace inverse of the reluctant matrix or the resolvent matrix. Okay, now this is represented as e raised to at. Hope you understood how you got this as e raised to at. So this is the properties of. Now next is the properties of phi of t. Now phi of t, since it is defined as this is equal to e raised to at. Okay, hope you understood this, how you got this. This is equivalent to 1 by s minus a. If you do that, when you take the Laplace inverse, you will be getting this as e raised to at. Now instead of this you have a matrix, so this will be e raised to a t, capital AT. Okay, so phi of t is equal to e raised to at, and this is an exponential signal. So from the exponential property, you from the any exponential signal you can represent this as at plus a square t square by 2 factorial plus a cube t cube by 3 factorial plus and so on, right? You can write like this. Now that is the first property. So that is the first property. Now let's move on to the second property. It's quite simple anyway. So this is phi of 0. What is phi of 0? That means you are putting t is equal to 0, a into 0, which is going to be equal to an identity. It is equal to I, but I told you that this always represents a matrix, and there is nothing like 1 in matrix. In order to identify 1, we always represent this by I, meaning this is an identity matrix. So what is an observation from this from this identity matrix? That is, the state transition matrix at t is equal to 0 is nothing but it is the identity matrix. Okay, now let's move on to the next one, which is now the third property is, say phi of t is equal to e raised to at. Okay, now this exponential can be represented like this, right? At the whole raised to minus 1. And what is this? This is actually phi of minus t, right? This is phi of t is e raised to minus t. Phi of minus t, the whole inverse, right? Right? So phi of t is equal to phi of minus t, the whole inverse. Or from this you can arrive at a conclusion that phi inverse of t is nothing but it is equal to phi of minus t. Okay, phi of minus t. Okay, now the next property is, for example, if you have phi of t1 plus t2. So what is that? So that is e of a into t1 plus t2, or that's nothing but e raised to a into t1 into e raised to a into t2. Now what is e raised to t1? E raised to t1 is phi of t1 into phi of t2, right? So phi of t1 plus t2 is equal to the product of phi of t1 and phi of t2, right? Hope you understood. Because of the this comes because it is defined as an exponential function, right? So what about next? Number 5 is phi of t the whole raised to n. That is nothing but e raised to a into t the whole raised to n, or that is e raised to a into nt, or you can call this as phi of nt, phi of nt. Okay, now what about the sixth property? Say you have phi of t2 minus t1 into phi of t1 minus t0. Okay, so you can make use of this expression exponential into e raised to this is e raised to t2 minus t1 into e raised to t1 minus t0, right? So when you sum it up, you can do it by yourself and you will be getting a result t2 minus t0. Okay, right? So making use of that exponential properties, you can arrive at the following properties. This is a very important thing. Usually the questions are asked based on this, directly asked as properties of STM. So these are the properties of STM. Okay, so here is a question for you. So questions can be asked in this way. Say a system is given in such a way that consider a system matrix given by A is equal to 0, 1, minus 2, minus 3. You know what A is because it is the part of the state equation. X dot is equal to A into x of t plus b into u of t. Now in this question, in our question, this A is given and you are asked to find out what e raised to at or the state transition matrix. So that's going to your matrix, and this is very important. Now okay, so how to proceed this? Now what is this e raised to at? How e raised to at is defined? E raised to at is defined as the Laplace inverse of si minus a inverse, right? Okay, so or you can say that in writings you can say that it is the Laplace inverse of what? The Laplace inverse of the reluctant matrix, right? Laplace inverse of the reluctant matrix. So first of all, what you want to find out is you need to obtain what is this si minus a. Okay, now this is this quantity is you will be obtaining by using this. A is a matrix, so definitely this has to be a matrix, and this quantity, this matrix has to be the order of this matrix, because this is a subtraction. For a matrix, if two matrices to subtract, the order has to be the same. So if that is the case, now we know that from the question A is a 2 by 2 matrix, so SI has to be a 2 by 2 matrix, right? Has to be a 2 by 2 matrix. And what do you mean by I? First of all, let us see what is I. So you need a 1 by 1, a 2 by 2 unity matrix. Now what is a unity matrix? 1 0 0 1, the diagonal elements of 1. So this is I. So what must be your SI? SI is multiplying each element by S, so you will get S0 0 S, right? So if that is the case, what is your SI minus A? SI minus A will be equal to S0 0 S minus what? Matrix A is 0 1 minus 2 minus 3, right? So you can do the simple element to element subtraction. So the matrix becomes S, then the next is minus 1, next element is plus 2, now this is S plus 3. Okay, so you're going to get S minus 1, 2, S plus 3. So that is your Si minus A. Now what is your next step is to find out its inverse. Now how to find out the inverse of this? Okay, so in this problem I will be writing you what is how to find out Si minus A inverse, and it is defined as, okay, the transpose of the cofactor of Si minus A. Okay, Si minus A, that is the transpose of the cofactor matrix. Okay, I will explain what is this cofactor, divided by the determinant of that matrix. Okay, That is, say for example, if you want to find out the matrix X inverse, it is nothing but it is the cofactor, the transpose of the cofactor matrix of X divided by the determinant of X. So that's what you are applying here. Now how to find out the transpose? The transpose of this matrix. So first of all, let us see the cofactor of Si minus A. What is the cofactor of Si minus A? How will you find out the cofactor? Now the finding out cofactor is, see, this is Si minus A. Say considering this element, delete the rows and columns, and you can see that S plus 3. So this is plus S plus 3. When it comes to this side, this is the negative, right? This represents negative anyway. So this is S into what is the cofactor of this? Minus 1. The cofactor of minus 1 is actually, when you take this becomes 2, right? Cofactor of, right? So this is minus 2, right? It is the negative of the cofactor is minus of that, minus of this element. Now coming to this, again you have a negative of this. So this is minus 1 or plus 1, right? And finally the cofactor of S plus 3 is S. Now you need the transpose of this. Now what is the transpose of this? The transpose of this is the cofactor transpose will be what? Will be S plus 3, 1, minus 2, yes. Okay, so this is it. So this is the cofactor matrix. Now what is the determinant of this? This is the cofactor matrix. Now what I want to find, so this is S plus 3, 1, minus 2 and S. Okay, so this is how you need to find out the cofactor. So if you have any doubts, you may refer your lower classes textbooks. There you will understand how to find out the cofactor of each matrix, of a matrix. So this is the cofactor, then finding out the transpose. This is what we need. This divided by now what is Si minus A inverse? Si minus A inverse is this cofactor, the transpose of the cofactor divided by the determinant of Si minus A. This is your Si minus A. What is the determinant? S into S plus 3, okay, minus of minus 2, that is minus 2, right? Plus 2, right? This is plus 2. Okay. Okay, so that is S plus Si minus A. Si minus A is S into S plus 3 plus 2. Okay, so this is inverse is given like this. So that means you will be writing this as S plus 3 matrix 1 minus 2, yes, right? It's the matrix divided by, okay, now you can have this as S square plus 3s plus 5, 3s plus 2. So that can be written as S plus 2 into, you can factorize that as S plus 2 into S plus 1, or Si minus A inverse, or what you want to find out is e raised to 80, or the STM is given by, okay, you can this is actually the determinant value, and you can take it inside the matrix, so that this term will be S plus 3 by S plus 2 into S plus 1, right? Then 1 divided by S plus 2 into S plus 1, right? Then next is minus 2 divided by S plus 2 into S plus 1. Then you have S by S plus 2 into S plus 1. Okay, so this is actually your Si minus A inverse. But is it the STM? No, it is not the STM. STM is the Laplace inverse of this. All the elements in this is in S domain. We want it in the time domain. That is, you are to find out the Laplace transform of Si minus A inverse, right? Or it is it is a that is what is called as phi of t or STM. That is, you need to find out the Laplace inverse of each element. So consider each element separately, and you know how to find out s plus 3 by s plus 2 by partially resolving this. You will be getting this as you can resolve this partially. You may do that by yourself, each term partially resolve, and you will be able to get 2 into e raised to minus t minus e raised to minus 2t, then e raised to minus t minus e raised to minus 2t. Okay, then this is minus 2 into e raised to minus t plus 2 into e raised to minus 2t, and this will be minus e raised to minus t plus 2 into e raised to minus 2t. Okay, hope you have understood. That means what I meant to say is, say you need to do this like this: s plus 3 by s plus, to take the first term and expand this, resolve it into partial fraction. Okay, that you know. And multiplying throughout this, find out a and b. So do that thing for each element and obtain this result. So now this matrix is in time domain, or that matrix we call as the STM, or the state transition matrix. Okay, now the next portion is the transfer function from a given state model. So as we start itself, we have studied a block like this. Okay, from the starting point itself, that is, we consider a system with the u of t as the input, x as the x of t as the state variables, and y of t as the output. Now what is basically the transfer function? Now transfer function has got only one definition throughout the whatever may be, whether it is a simple system or in a state model. Always the transfer function is nothing but it is the Laplace transfer of y of s to u of s. Here the input is u of t, y of t. Now taking the ratio of this to output to input is what is called as the transfer function. That's what we are going to study. Now, from this, we know that from a state model, this is a system. You can have the state model. State model is the state equation is given by ax plus bu, where a is the input matrix, b is the a is the system matrix, while b is the input matrix. And not only that, you have again y of t, that is y of t is equal to c into x plus du, right? C into x plus du. Now let us start from this state equation. Now in order to get the transfer function, what you need to do is you need to find out this, take the Laplace transform of this. Okay, now taking the Laplace transform, we know that this is x dot, this is equivalent to dx of t by dt, right? So if it is equivalent to dx of t by dt, and we know that when you take the Laplace transform of this is s into x of s. So x of s minus x of 0 is equal to a into x of s plus b into u of s. Now you can bring this x of s to this side so that it becomes x of s into si minus a, right, is equal to b into u of s. Or bringing this to this numerator side, this becomes the inverse. So since it is a matrix, when it comes to this side, this matrix becomes si minus a inverse b into u of s, that is your x of s. Okay, so this is an important thing. X of s is si minus a inverse b into u of s. Okay, taking the say y of t is equal to, we know that this is cx plus d into u, or y of s is equal to c into x of s plus d into u of s, right? Okay, so d into u of s, or what is the c into x of s? From this x of s we have already found out as si, substituting that value, si minus a inverse into b into u of s plus d into u of s, right? Okay, so you can take this u of s outside, so that taking u of s outside, you will get this as c into si minus a inverse into b plus d, right, is equal to y of s, or what is y of s to u of s? Y of s to u of s, which is actually your transfer function, which is given by c into si minus a inverse b plus d, which is, even though it is called as a transfer function, this is also called as, this is anyway, this is going to be a matrix. So more than being a transfer function, it is called, generally called as a transfer matrix. Transfer matrix. Okay, so I warn you that you should not get confused by STM, that is state transition matrix, and transfer matrix. Both are different. If you are asked to find out state transition matrix, the first thing that you need to find out is Si minus A, right? Look at this, look at the problem which we have done. So first of all, what you need to find out is Si minus A. Then you take, after Si minus A, you take the inverse of this. Inverse is the cofactor of that Si minus by the transpose of the cofactor divided by the determinant. And when you do that, that is your Si minus A inverse. Now, that is not the STM. If you want the STM, you need to find out the inverse of that Laplace, inverse Laplace transform of the metric elements in the matrix. So thereby you will be getting STM. While this is, while the transfer matrix is given by C into Si minus A inverse into B plus D, where C is the, C is called as the output matrix, A is called as the system matrix, while B is called as the input matrix, and D is called as the coupling matrix. Okay, right? So this is your transfer matrix. Okay, so let's try to do a problem. So questions can be asked in this way. You will be given with the matrix A, B, C and D. Here usually in almost all the questions, the coupling matrix will be 0. So it makes the things a bit easier. So A, B and C. Now you are to find out the transfer matrix. That means you need to substitute in this. So the first thing that you need to find out is Si minus A. Okay. Now look at the, first of all, what you need to do is look at the order of this matrix. This is a 2 into 2 matrix. So you need an identity matrix like this. So your Si minus A will be like this, right? This is S into 1, 0, 0, 1. This is the matrix, right? This is the identity matrix. So this is S into I minus the matrix minus 3, 1, 0, minus 1. This will be equal to S0, 0S minus minus 3, 1, 0, minus 1. So you will be getting this as S plus 3, right? 1 and 0, then S plus 1, right? S plus 1. So this is actually your Si minus A. And what is the, how will you find out the inverse? The inverse is, the inverse of this matrix is the transpose of the, so what you want to get is the cofactor. Now the cofactor matrix will be, how will you find out the cofactor? This cofactor will be S plus 1, okay, that is 0. Then here also it will be minus 1, and this will be S plus 3, right? This transpose, so this is the cofactor matrix transpose by the determinant of Si minus A, right? Okay, so Si minus A is this, the determinant will be S plus 3 into S plus 1. This is the determinant of Si minus A. Now what you need to do is the transpose of this. So the transpose is going to be, so this is Si minus A inverse is nothing but the transpose is going to be S plus 1 minus 1 0 S plus 3, okay, divided by the whole divided by S plus 3 into S plus 1, S plus 3 into S plus 1. Now you can since it is a determinant, you can divide this each element by this determinant, so that this becomes the matrix becomes 1 by S plus 3 minus 1 by, next element will be minus 1 by S plus 3 into S plus 1, this is 0, and the last element will be yet 1 by S plus 1, right? So this is actually the inverse. Now what is the next step? Next step is to find out what? So this is actually S plus Si minus A inverse. Okay, now this is it. Now what you need to do is you need to multiply this by C. Okay, so the answer is 1 by S plus 3 minus minus 1 by, okay, so let me check. This is okay, this is minus of minus, so here you have plus 1. It's not okay. When you take the cofactor of this and this, there will be a negative sign, and this negative and this negative becomes positive, so this is plus 1 by S plus 3. Now this is it. Now what you want is you want to multiply that by what you need to get is you want to find out S into Si minus A inverse, right? So sorry, C into, what is C? C is given as a raw matrix 1 into 1 into 1 by S plus 3, 1 by S plus 3 into S plus 1, right? Then 0, 1 by S plus 1. Okay, so this is a 1 into 2 matrix, right? This is a 2 into 2 matrix. So when you multiply this is multipliable, and that will result in a 1 into 2. Okay, so that will result in a 1 into 2 matrix. That means with 1 row and 2 columns, right? So the first element will be 1 into, so this will be so this will be 1 into 1, so this will be 1 by 1 into 1 into 1 by S plus 3 gives you 1 by S plus 3, right? Okay, 1 by 1 plus S3. This will be 1 by S plus 3 into S plus 1 plus multiplied plus 1 into 1 by S plus 1. Okay, now this is your C into S minus A minus 1, and what is your transfer matrix? The transfer matrix D0. Now the transfer matrix is actually equal to C into Si minus A inverse into B. That is this matrix 1 by S plus 3, and this can be written as C 1 plus S plus 3, right? Or you can call this as S plus 4 divided by S plus 3 into S plus 1, right? So S plus 4 into S plus 3. Okay, so this into B. What is B? B is again a column matrix 1 into 1, right? So this is a 2 into this is a 1 into 2 matrix, while this is a 2 into 1 matrix. Okay, so this is again a multipliable, so this is going to be a single answer. What is that? This will be 1 by S plus 3 plus S plus 4 divided by S plus 3 into S plus 1. The answer is going to be, when you take the LCM, S plus 3 into S plus 1. This will be S plus 1. Okay, S plus 1 plus S plus 4, or you will get this as 2S plus 5 divided by S plus 3 into S plus 1, which is your transfer matrix or the transfer function of the system. Okay, hope you understood. This is quite simple. Questions can be asked in this way. Okay, so the same question can be asked in a different way. Determine the transfer matrix for the system given below. So here the system model is given. System model means you are given with the state equation and the output equation. Now you are asked to find out the transfer matrix. Okay, do remember, I again repeat, make sure that either whether it is STM. What is STM? STM is actually your state transition matrix. This is transfer matrix or the equivalent of the transfer function. Now if you want the transfer function, you know the expression of the transfer function. What is that? The expression of the transfer function is C into Si minus A inverse into B into D. So you need all the matrices. Now from the state equation, you must see that this is given in such a way that this is of the form x dot is equal to ax plus b, right? So what is this matrix? What is this matrix? What is this matrix? This matrix is A matrix, this matrix is B matrix, and this is C. There is no D, so you need to assume D to be 0. So using these three matrices, making use of this expression, okay, making use of this expression similar to this, okay, you can find out the transfer matrix. Okay,